This Pauling-Hellman algorithm is good for finding the value x in this equation. So let's say we know a prime number p for our modulus and alpha and beta. So we are looking for certain integer satisfying that alpha to that integer is congruent to another integer beta modulo p. And if p is really small number, then we can just do try and error method. So saying p is 11, then we can just plug 0 to 10 for x to find this result. But in reality, we are looking for really huge prime numbers, this one, like 100-digit prime numbers like that. Then this try and error method is kind of useless. So this Pauling-Hellman algorithm giving us a really nice and fast way to find this x. And in this video, I'm going to explain the whole behind the mathematical ideas of it. It might be a little bit difficult to follow it, but I really recommend to do by yourself. Just bring your pencil and paper and try to follow this proof for yourself. And the next video, we are going to handle one example to apply this algorithm to find the x in certain real cases. Then it might be much clearer how it works. Okay, so let's try to see. First of all, our p must be a prime, and alpha, beta must be kind of any integer in this group, which means they must be relative prime with 1. That's the condition. And p minus 1 is not a prime number, clearly. And of course, p is a big number, then it's not 2. So all prime numbers are odd. So p minus 1 is at least even number. So one of its factors should be 2. Okay, it's a clear one. But we don't know how many factors we have for that number. So let's just pretend p minus 1 is factor to pi to the ci, p to the c2, and up to that much. So clearly these pi's are distinct primes, and ci's are positive integers. So we're just looking for one of them and to find to show how to find that x for that. Okay, so the remaining part is exactly the same. So you can say p1 to c1 instead of pi to the ci when you see this video. So let's just pick I randomly, or we have to run through all together, but just pick arbitrary one, and in your mind it's just pi ci. It's okay. And for easier notation, let's just change pi to q and ci to c. So from now on, qc, the small qc's that chosen prime number and its power. So the first task is we are looking for the solution for this equation. The x, what you are looking for, which is not unknown at this moment, is congruent to xq for modulo q to the c. So it could be p1 to the c1, and this small q is just a notation. This number is related to this factor, not the whole p. Okay, then we could write this xq, the results of that, like this. The sum of aj times q to the j, and j is from 0 to c minus 1. Once again, this q is pi, right? Whatever the prime number is. And c is the power from this factorization of p minus 1. So it's at least 1, because ci must be positive integer, right? So with that condition, this sum is reasonable. We should have at least one term, right? But it could be many terms like this. Depends on what power c we have for that prime factor pi, right? Anyway, so aj is unknown at this moment, right? It's just to denote like this, and it's end with q to the c minus 1, because if it's more than this, then the term should have q, then it should becomes 0 for this modulus, because that number x sub q is for modulo q to the c. Okay? So that should be good for notation for this x sub q. And another thing is ai, the coefficient for each q, the powers of q's must be from 0 to q minus 1, because if any ai is q or more than that, then we should change it, because we are looking for just congruency with that power, right? So all we need is just 0 to q minus 1 for this coefficient for this equation. Okay, then in this equation, our x sub q is congruent to that x what you're looking for modulo q to the c, which means xq can be written, the x itself can be written by x sub q plus the powers of q to the c, right? That's could be extra terms. So our x can be written by this. xq is from here, it's exactly copy of here, and plus some integer s times q to the c. That is what we are looking for, right? So we are just wonder what kind of AI is satisfying that. So let's say from that given equation that is given in the question, beta is congruent to alpha to the x modulo p. If we put this p minus 1 over q as the power for both sides, then they are congruent for modulo p. And instead of x here, we already found that can be written by this, right? And instead of this part, because all these terms has q as a common factor, we can say just simply k times q for that. K is any integer from there, so we can change it like this. Then we can separate this alpha to the a0 plus kq to alpha to the a0 times alpha to the kq, and put this power for both. Then this whole thing changed to the product of these two terms. That's good. And from Fermat's-Little theorem, or extension of that is Euler theorem, that alpha to the p minus 1 is congruent to 1 modulo p. So this part becomes 1. So we don't need it. So this whole number is congruent to this notation. So once again, beta to the p minus 1 over q is congruent to alpha to the that modulo p. So that's what we have. And because of this, look at here, we know all these numbers like a p, alpha, beta, q. So a0 is the only missing one. And right now, this we can calculate this a0 easily from there. And you will see in the next example for that. Okay, the next step is when we talk about this x or xq, it's combination of these ai's, and we just to find out the first term, the constant term a0. So we need to looking for all the other coefficients for xq. So let's define beta 0 is congruent to alpha to the x modulo p, and the beta j is beta times alpha to the negative of that. Okay. So look at the notation, this j makes this much. So we just cut down all the other ai's, okay, the terms which has greater than or equal to j as its notation. So if j is 1, then beta 1 becomes just the beta times alpha to the that much, right? Negative a0, because we are not going to accept q to the 1 because j is 1, so we can only accept q to the 0, so it's only constant term. So that's our beta 1. So you can imagine what beta 2 means. Beta 2 means up to this much, right? and there is no such thing. So like that. Okay, then from that equation, just put this p minus 1 over q to the j plus 1 on both sides. Once again, from the equation, so beta j is same as this one, right? And just put these new powers on both sides. Then the right hand side becomes this, because beta was congruent to alpha to the x, right? And this part multiplied by that, so we can put together and it becomes alpha to the x minus that. Then x itself is a0 up to this plus sq to the c, right? So we can cancel out this first I terms, right, from x, and these are the remaining parts of it. Then inside here, except the first one, from the second one we have q to the I minus 1 as a common factor for all these terms, right? So we just put these remaining terms together. You can say k times q to the j plus 1, and that is j this moment. Okay. Then we already saw this case before. We can separate this alpha to the this one times alpha to the that second power, and we apply this one over there. Then the first one becomes alpha to the this. Okay. Carefully, and after cancel out q to the j here and here, we only remain in q for denominator, and aj become here, and p minus 1 becomes there. And the second part, after multiply this, we can cancel out q to the j plus 1 from numerator and denominator. Remaining one is only kj times p minus 1. Sorry, it's typo. So once again, this form looks like alpha to the p minus 1, which is congruent to 1 for modulo p. So we can just cancel out and remaining this. So no matter what j is, we have formula for that by this. So that becomes our formula. And in this formula, the good news is if you apply j is 0, then the result is exactly the same as the one we found here. So we can generalize these two parts into just one, make one formula. Okay, so that's what we get. So just apply this rule all together. We can find all AJ's, right, and B1's. So that's how we can find the whole X. So far it may not clear, so it's better to play with some real cases, then it's going to be much more clear, and you can apply same procedures for some other cases.